Hello, everyone. Do you hear me? You hear? Yes. How about the others on Zoom?
Yes. Yes.
Wonderful. So we're ready to start. We are studying the MAC layer. So what we will see in this first minutes is MAC layer that is based on random access. Random access is really at the heart of the MAC layer and how it is today. And I have described this very primitive form of random access that still exists in some systems today, which is called ALOA, where you simply send, wait for an acknowledgement, and if there is no acknowledgement, you take that as a symptom of a collision. Ethernet was using a similar principle in its very first implementations. The very first implementations of Ethernet were like shown here. You have a big cable and multiple stations connected to the same cable, with a difference with respect to ALOA. With Ethernet, we assume that the medium is transitive. Transitive means everybody on the cable can hear everything that is happening, which was not true with ALOA. If you are on an island in the east, you don't necessarily hear if an island in the west is sending traffic to the center, because you're too far away, you might not hear it. In Ethernet, the engineers made the assumption that everybody must be able to hear everything on the cable. That means the cable is not too long, such that if a station that's at the far left sends a packet, then the station that's at the far right will see that there is a packet being sent. So the signal noise, the signal to noise ratio will be large enough. Ethernet cables were typically not too long. Initial Ethernet deployments have a maximum of 2 kilometers. So this coaxial cable could be up to 2 kilometers, and you can still run it today if you have a special need. Today, Ethernet cables are limited to 100 meters. Given that the medium is transitive, we can be a bit smarter than ALOA. With ALOA, we send and hope there is no collision. But if we can hear collisions. So the idea is simply that one. The algorithm is given here. You try a number of times. We have one packet to send. That is the code that you run when you have one packet to send. You will try at most max number of times. And before sending, you listen whether the channel is idle or not. If the channel is idle, that means nobody is speaking, and then you transmit. You wait for an acknowledgement, and if you receive an acknowledgement, you're done. Otherwise, you try again, like with ALOA. What do you think that this produces? Can there still be collisions? Small speak-up question. I close the poll. In a few minutes. Okay. I close the poll. The majority says C, it can occur in any case, but a large minority says no, it depends on the bandwidth delay product. So let's see what the truth is. Here is the answer. It may always happen. So here I'm showing again a space and time diagram where time flows vertically and space horizontally. And you see what happens when a packet is sent by A and at about the same time by B, then there are points on the medium, on the cable, where there is really a collision. The points on the medium where there's a collision are the points where the two shades overlap. So this can always happen, even if you listen, because of course, by the time you listen, since propagation is non-zero, this would never happen if propagation would be zero. But since propagation is non-zero, You listen, nothing happens, therefore you can send. But by the time you send, of course, things have changed. So the fact that in distributed systems, whatever you do here, you can never be sure of the state of the rest of the system because there is a non-zero propagation time. That, of course, makes distributed systems interesting. And in this case, it means that collisions are always possible. You cannot guarantee that there will never be collisions. But of course, by listening, and if the cable is not too long, that means if the propagation time is small compared to the transmission time, which is the case for small bit rate, small bandwidth systems like original Ethernet, like power line communication today, where the transmission rate is 10, 20, 30 megabit per second over cables that are perhaps 100 meter, then the window during which you're vulnerable is the window of propagation time. So it's the order of microseconds. So there is a small chance during a few microseconds that your decision is wrong, but if the decision is right, you will spend lots of microseconds, probably milliseconds, transmitting the packets. So the fraction of time that is vulnerable is small, and analyzing the maximum performance of CSMA shows that you can do much better than ALOA. In fact, Ethernet is doing exactly this, and Wi-Fi is doing exactly this. All medium access protocols are doing this, with, of course, various bells and whistles that are specific to each system. In the case of Ethernet, here is what the code of the station is. For some reason, yes, it keeps moving. You add another system in Ethernet, which is shown on the left, is that in ALOA and CSMA that I've shown, you interpret the acknowledgement as the absence of collisions. In Ethernet, for some reason, that is based on the fact that we assume the medium is transitive, we can know whether there's a collision because we can hear what is happening. So I decide that the channel is idle, I start to transmit, but if I was wrong, I will detect that I'm wrong. So by detecting it, I know there is a collision. So this is why we don't wait for the ACK. There is no ACK in Ethernet. Instead, we continue listening while we transmit. And if we detect a collision, we stop. We do a few other adornments to that. We don't simply stop. We send what is called jamming bits. The goal is to make the collision long enough so that it can be reliably detected. If you're unlucky and you can hear only a fraction of a bit that is in collision, the collision might be detected by you, not by someone else. So that might cause problems with someone else that is sending and does not detect that there's a collision. So you send what is called jamming bits to make the collision long enough. But we can ignore that as a first approximation. So this is Ethernet. For many people, this was Ethernet for many years. This is how it works. Let me illustrate again a time and space diagram. Here I'm showing A, that is sending a packet. B senses, listens, and see that nothing is happening. So B decides to transmit. But we see also that very shortly after starting to transmit, B sees that there is a collision. Therefore, B stops transmitting and will back off, will wait for some time. That is long enough. A will do the same. On A side, there will be at a different time, but during, roughly speaking, the same round trip time, A will also sense the collision and will draw a random back off. T1 and T2 with small probability could be the same, in which case there could be a collision again, but with large probability, they will not. So one of the two will back off, and while you back off, you don't listen, you don't transmit, you do nothing, you're frozen. So here, one of the two will win, B in that case, so B will transmit, and the back off time is computed such that it is large enough that these race conditions will not occur again. So if B has drawn a smaller back of time, B will win, and A will now, before trying again, A will see that there is B transmitting. So at time T1, when A wakes up, it sees that B is transmitting and will wait until the transmission is finished. This is CSMA-CD, which is the variant of the random access protocol used by old-style Ethernet. If you think about it, there is a small problem with that, which is illustrated on the left. On the left, I'm showing A that is sending a packet, and B also listens, but there is a collision, so sends another packet. And B sees that there's a collision, so will stop transmitting after some time. And there will be a collision also for C. If the intended destination of A is C, for example, C will receive garble, will not properly receive the packet. But A did not see the collision. Because if you look the space and time diagram at A, you see that the two packets sent by A and B come at different points in time. They don't overlap. So for A, there's no collision. Seen by A, the radio wave that comes to A are nicely separated in time. For A, there's no collision. So this is a case where what I said before fails. A, we say with CSMA-CD, since the medium is transitive, if I can transmit, I have to listen, and if I know there's no collision, I'm happy, I think the packet has been transmitted. But here, we see that the collision was not perceived by A, but it existed somewhere on the channel. The problem, if you think about it, can occur only when transmissions are very short. So this is when B sends a packet that is too short here. So this may happen if packets are too short, and this is why on Ethernet there is a minimum packet size of 64 bytes. Now, when Ethernet was invented, 64 byte was large, headers were small. Now IP headers are larger because we have IPv6 and not IPv4. Plus, we typically have a security layer that we did not have at the beginning that will add many, many bytes. So in practice, you typically have packets that are larger than that. But some industrial systems, real-time systems that send small messages might have packets smaller than that. So if your packet is smaller than 64 byte, you have to do what is called padding. You add zeros or random bits in your packet to make it long enough. And then, of course, you must have a mechanism to know that there is padding here. So this is, as I said, the historical Ethernet. It's also called half duplex. Duplex means a cable that can be used in both directions. The radio channel of Aloha was not duplex. There was one channel for the downlink and one channel for the uplink. Ethernet is duplex. The same cable is used for communication in both directions, but it's called half duplex. This version of Ethernet is half duplex because it can work in both directions, but not at the same time. Because if there are packets sent at the same time, there is a collision, and the goal of CSMA-CD is to prevent those collisions. So this is half duplex Ethernet. Wi-Fi is very similar with zillions of complications. I mean, the standard of Wi-Fi is almost 3,000 pages, so it has zillions of complications. But I will say the main thing that is interesting for us here, it is like Ethernet, and it inherits all its properties from Ethernet. It was built and engineered on the experience of Ethernet, with one main difference. Here you cannot make the assumption that the medium is transitive. Because even if Wi-Fi in this room, even if the radius of your LAN is not very large, you can never be sure that, for example, when A sends a packet to B, that C sees this packet. Right? Typically, because of what is shown here, A is just at the limit of being able to reach B, but C is also just at the limit of reaching B, so the distance from A to C is very large. So the signal attenuation from A to C, which in open space grows like a power of 2 or 3 with the distance. If the signal would be radiating in all directions, it would decay like a power of 3, but here it decays like a power of 2 dot something, which means if you're far further away, the energy is diluted in more space and you get less. So inevitably, C will not receive or might not receive the information. This is why in Wi-Fi, there is an additional mechanism called the RTS-CTS, request to send, clear to send, where before sending a packet, you send a very short preamble. And the typical design is Wi-Fi has been done works in peer-to-peer mode, but has been designed really to work originally with a base station. So you have a base station that's at the center. When A wants to use Wi-Fi, it has to be within reach of the base station. And C also has to be within reach of the base station. So when the base station receives a request to send from A, for example, it will broadcast, send over the medium, a clear to send that anybody who is within reach of the base station will receive. And that is the attempt to make the medium transitive. When A starts to speak, this clear to send, which is repeated by the base station, will be received by C. And if C was hoping to send something, C will be blocked from sending. So C is not actively listening for transmissions from A, because that might not work, but is actively listening for anything that the base station might send. If the base station sends a clear to send with the destination address of the clear to send, which is not C, then C knows that that station cannot transmit. There are other optimizations. We'll see some of them, in particular in terms of MAC addresses. But as a first approximation, this is how Wi-Fi works. Small question that is of interest for us from the viewpoint of protocols. In a Wi-Fi network with a single channel and a single base station, so in this network that is shown here on the board, how many frames can be transmitted concurrently? And I propose several solutions, depending on whether the uplink and the downlink could be used simultaneously or not. I close the poll. The poll has closed spontaneously. Interesting. Okay. So I reopen it and close it now. So the majority thinks C, which would mean there is an uplink and a downlink. They are on different frequencies and they don't interfere. But that's not the case. That's not the case with Wi-Fi. Although it was designed with the idea of a base station, in that sense, the channel is peer-to-peer, so the channel is the same. It's the same channel that is used in both directions. So the CTS is not sent over a different channel than the RTS, for example, here. Which means, concretely, that there is only one. So the correct answer is A. Which is in line with what we said. We have one channel, and the MAC protocol is making sure that only one packet can be sent at the same time. In that viewpoint, the base station is not a different system. We will see some implications of that in the design of LANs that use Wi-Fi stations. So the story of this section 1 is the original story of the local area network. And this is really the one that has shaped the MAC layer and the way it is today. Even the name, MAC, stands for Medium Access Control. But local area networks that are based on Ethernet are completely different today. They don't use any of the things we have seen before. And how did we come to that? This is how I will explain here. So Ethernet was originally, like the top shows, but today it is not. Today, Ethernet is based on switches. In the lab, you will see we connect with mininet switches. If you at home connect over wired infrastructure, you would connect to an Ethernet socket somewhere. So what is a switch? Well, a switch is a queuing system. The very first switches were PCs, where the processor would have one Ethernet, large number of Ethernet ports, and it would do the following. Whenever a packet comes into the switch, it is buffered. Then the processor analyzes the destination header and then sends it to the output. This is also what a router does, except here it's for Ethernet, so it looks at MAC headers and not IP headers here. When we do that, there is no CSMA-CD. The link, the cable between A and the switch here is works in both directions. So there is no protocol. We simply have a cable. And you see the blue input buffers and the green output buffers. They are managed completely independently. When A has something to send, it sends it over the wires that go to the switch. The switch receives them on the blue buffer. When the switch has a packet to send to A, it sends them to the green buffer that go over separate wires to A. And A also has a receive and a send buffer. So this is why we call this full duplex Ethernet. The cables are full duplex. We keep the name Ethernet, but there is no, and we keep the name MAC protocol, but there is no MAC. No collision that could occur. Instead of collision, what do we have? We have queuing. The processor, if it's a process, today modern switches are based on dedicated circuits. It's not based on a processor, but they are big queuing systems. And if many packets go to the same port, for example, if A and B send a packet at the same time to C, and if the lines are all at the same speed, for example, 1 gigabit per second, then obviously the two packets cannot go out together to C. So they will be queued. They will stay in the green buffer for some time. So there is typically output queuing in all switches. If we would design the internet today, we would probably not invent the MAC layer. We would say, but a switch, that's what the router does. So why should I bother about the MAC layer? I can connect my PC or my station or my printer. If I connect it via cable, I would need the MAC for Wi-Fi, but for cable system, I would connect directly, and then I send with a point-to-point protocol with an IP header, and this should be a router. This is how we would do things if we would start from scratch today with IPv6. Remember, IPv6 has automatically allocated link local addresses, so there would be no need for all this MAC header and all that stuff. But it's not the way it is. And once something has been done in communication networks, it takes a very long time to modify it. For example, IPv4 is obsoleted by now. The official standard is IPv6 and has been so for several years. But most of things we do are still with IPv4. So same thing. The MAC is here to stay, and people have built things around the MAC layer that we will see some of them today. So it will stay the way it is, driven by history. Incidentally, that shows what happens when you try to be backwards compatible. The MAC layer that is designed today wanted to be compatible with what is shown here. What is shown here is on the left a concentrator. What is a concentrator? It's something that doesn't exist anymore today. You can buy some. We have some in our lab if you want to play with them, but practically we don't use them today. But those concentrators existed 20 years ago when people started to observe that having a coax cable that goes from one place to the other is a very bad idea. It's a very bad idea because cabling problems are very difficult problems to debug. They are difficult because you need to physically be on the cable to see what goes wrong. You might remember, I think 1 or 2 weeks ago, we had a cabling problem with the beamer, and we had to have somebody come and inspect the cables to find that there was a socket that was loose. So this happens with the first network. So the first networks were Ethernet and token ring that were all shared medium. Enterprises started to deploy them, and they started having problems. Once you have a network with not 3 or 4 stations, but 5,000 stations, like Ethernet, token ring cables, IBM had LANs with that size. And then you have one cable somewhere that's loose or broken or something, then it's a nightmare. You need to inspect everything. If the network is large, that will happen all the time. So what people invented immediately after recognizing this problem is concentrator. What is a concentrator? Well, it is something that has the cable, the shared medium is in the box, and the rectangles are repeaters that repeat the signal electronically and can be monitored with a LED and with remote control. So if anything goes wrong on the cable, you will know between which boxes the thing goes wrong. So you will know whether it is my PC, the cables that attach my PC to the box that don't work because the LED is not working, and that can be pulled remotely by somebody working on a computer. So we started breaking this shared medium into lots of small pieces of cable that could be individually monitored here. And that was how immediately the first commercial LANs were deployed. Then people immediately thought, but instead of doing this, why don't you put a switch inside, a queuing system? Right? That would be much better because in a queuing system, we have full duplex links. And also, if we have A that sends to B and C that sends to D, the output queues are not the same, so those two transmissions could occur in parallel. Right? So performance is dramatically larger. But when people did that, they wanted to be backwards compatible with the concentrators. So they imposed that the bridges are transparent. When we put a bridge, which is a switching system for Ethernet cable, there should be no difference for the stations that are connected to it. They should not know whether they are talking to a shared medium or whether they are talking to a bridge here. And in particular, the format of the packets should be exactly the same. This is why there is no TTL, for example, in the Mac layer. Because there was no need for TTL, we have a shared medium cable. A packet can never loop, for example. So here is how bridges work. A bridge has, like a router, has a forwarding table. We don't call it a routing table because it's not a router. And also because it doesn't use longest prefix match, but exact match. Because the MAC addresses that we have seen already a few weeks ago, the MAC addresses don't have any structure. They are just hardware addresses. They are testimony to where you bought your machine from, but not where your machine is. So a bridge has a table, like the table I'm showing here. It knows that MAC address A is on port 1, or interface 1, MAC address B on number 2, and MAC address C on number 3. And when a packet comes, sent by A with destination address C, for example, well, it knows in which output queue it has to put the packet. So it is like a router, but it does an exact match here. How does a bridge build this table? Well, of course, you can, in Mininet, in the lab, you can manually go into the bridge and write the values of the table. But this is not how people wanted it to be, because again, a bridge should just be a high-performance concentrator. If you have a concentrator, which is just cabling electronics added to cabling, you don't configure anything in the concentrator. So the bridges should be completely plug and play. Unlike routers, in a router, you need a lot of configuration. The router needs to know what are all the, you need a numbering plan, you need to do subnet, decide on subnet masks, subnet prefixes for all the different ports of a router, etc. You have to design things. For a switch, we don't want to do this. It should be plug and play, and you can do this experiment if you have an Ethernet cable at home and you want to extend This cable, for example, if you have a box that has only 4 ports and you have 6 machines to connect, you can buy an Ethernet cable and buy an extra switch that you get for 30 francs from Migros, and then it will have the function of a port extender. When you do that, you have the impression you're just doing a port extender like you do for USB, for example. But what you're really doing is you're putting a switch there. So how does the switch build its table? Because then your switch will know which MAC address is on which port. How will it know? Well, with this simple method, it will observe all the traffic and learn. When A sends a packet to C, then there is a source MAC address. So the bridge will see, oh, this is coming on port 1. So the source address that's on port 1 is A. Therefore, A is on port 1. So it will write in its table, A is on port 1. Of course, there's a chicken and egg problem. How does A, when the first time A sends a packet to C, the bridge doesn't know where C is and where A is. So when it doesn't know, the frame is simply broadcast to all interfaces, except, of course, the interface that it comes from. So when you bought your switch from Migros, you install it for the first time. When A sends a packet to C, then the bridge will send it to B and to C. Will send it to all of its ports, which again is simply imitating what the shared medium Ethernet would be doing. On the shared medium, the packet is visible everywhere. It's just that you, at the destination, you see your address or not. So the bridge will do that, and the packet will reach C, also B, but if B is not a spy, B will drop the packet. And probably C will respond to A, but the bridge already knows where A is, so the response will not be broadcast. And when the bridge will see a response from C, it will also know that C is on port 3. This is how standard bridges work. I mentioned that you buy your little switch from Migros, so if you buy a switch from Migros, you're doing this. B3 is your ADSL modem that works as a switch, and you want to extend it, so you buy B1 and B2, for example, because you have only ports 1 and 3 on B3, and you want to extend it, so you do this. Does this always work? I saw, yeah. I close the poll, and I hope this time there will be no collision with other polls. So the majority says A, yes, because learning propagates, but unfortunately, no, that's not true, because there might be loops. Of course, the figure I showed was a tree. So on this tree, yes, it would work. But we would like to support loops. Well, you could say, why do you do loops in your cabling topology? Well, perhaps at home you would not do a loop. If you simply have one master bridge and you want to extend it, you connect 2 extensions, you don't do loops. But if you have a larger network, you might want to have redundancy in your network. You don't want to have a single point of failure. So if you have a larger network, for example, metropolitan area networks that use bridging are typically cabled as rings. In a ring, if any of the elements of the ring fails, there is always another direction. that makes the ring work. So one of the key things when you design a complex network is to avoid any single point of failure. So you want to add some redundancy. And a simple redundancy, for example, is the ring. So here is a ring that I built, so it's a different use case. If you have a ring, then of course the learning causes a lot of problem. I mean, first, when you have a packet that you don't know where to send, you send it on all ports. Then it will be received by the other bridges, also on all ports. I will send it on all ports, so it will create a flood of packets. It will flood all the net, so it will be an exponential number of packet duplicates that will be created. So this will not work. It will flood the network. Also, if there is a ring, that means if there are loops, that means there are multiple ways to go to the same destination. That's an equivalent property. For example, to go from A to D, we can go via B1 and B2, or the long way via B1, B3, and B2. So when the bridge is starting to learn, it will not know the bridge at B2, the bridge B2, when it receives a packet from A. You could say most of the time the packets will come from interface 4, but it might also come from interface 2, depending on perhaps the queue number 4 on B1 is congested. So it's not true. It will come for the longer way via B3, which is longer in number of hops, but might be shorter in time if the queues on this path are less congested. So you don't know. The truth is you don't know which way the packet may come, and worse, it may oscillate. It may sometimes come via one port, sometimes via another. So this simple learning bridge mechanism doesn't work if there are loops here. And the worst of all is the fact that you need to broadcast. That prevents loops from being a good idea here. Now you could say in the internet, we have lots of loops and we have routing protocols. I will take care of not using them. And if in a transient period of time there is a transient loop, then we have one mechanism to handle it. It's the TTL or the hop count, in the hop limit in IP headers. That will make sure that doesn't get too bad here. In Ethernet packets and in Wi-Fi packets, there is no TTL. Why is there no TTL? Because we want it to be backwards compatible with the original shared medium Ethernet. On the shared medium Ethernet, there was no reason to be a TTL because it's a single cable. It cannot create loops. So what do? We support loops in the topology, and every bridge, by default, at least the ones you buy from Micro or in software, the software bridges we have in the labs, we can disable this function of loop prevention or not. But by default, every bridge should do it because otherwise the bridging protocol doesn't work. It's called the spanning tree protocol. So all bridges, they talk to other bridges and they run a protocol between themselves in order to detect loops and break them. So for example, on this topology that is shown here, the red crosses are ports that will be disabled to avoid loops in the active topology. You could say this is stupid. I mean, first you create a network that has loops, then you break the loops. And you could say, yes, it is stupid, but still there is a good reason for doing that. If you create a network that has loops, this is because you want to be resilient to failures. So hopefully this protocol will adapt to changes in the topology. If one of the bridges or one of the links dies, the topology has changed. And if, for example, LAN B here, that is shown on the left, dies, which is an active LAN that is not eliminated by the spanning tree protocol. If this LAN dies, for example, because one of the two switches die, then the protocol will detect this and recompute another spanning tree. So it will adapt to it. Otherwise, of course, it would be stupid. How does it work? Well, it is described in this poem. This is a poem by Radia Perlman. Some people call her the mother of the internet. It's one of the big figures of the internet. And she is the inventor of the spanning tree protocol. And she explains this in this poem. I think that I shall never see a graph more lovely than a tree. a tree whose crucial property is loop-free connectivity. So we're just expressing that a tree is equivalent to saying that there is no loop. So how does it work? The tree must be sure to span. That's why we call it the spanning tree protocol. So packets can reach every LAN. That means the tree should reach all the bridges. It's a spanning tree. First, the root is selected. By ID, it's elected. So all the bridges talk to each other. This method is called gossiping. And they elect the one that has the smallest ID. So every bridge is configured. You can configure it if you want to configure it. Otherwise, if you don't configure it, it is simply derived from the manufacturer ID that is built. So it's a random number for you. You can influence this ID by changing manually the first bits of this ID, which are then treated as priority bits. Then I am a bridge. I speak to my neighbors and I say, I am bridge B1. And all my neighbors, all the bridges that I'm connected to, will know that I am B1. And they will also say what is their label. From this, I will choose who is the best. So if I have neighbors B3 and B4, I am the best. I know I am B1. And B3 will know that B1 is the best. So that's one hop. Then gossiping means we repeat what we know. So bridge B3 knows that the best so far is B1. So B3 will repeat this to the neighbors of B3. So all the neighbors of B3 will know that the best label is B1, and so on. Since the network is finite, if it is connected, all the bridges will learn that the best number is B1. So they will say, we have elected B1 as the root. This is the root bridge. So that's the easy part, gossiping. Then there is a fancy part that uses what is called distance vector routing, or the Bellman-Fold algorithm, that we will discuss in detail when we talk about one of the two routing methods used in routing protocols. Here it's not a routing protocol, but it uses the same method. The same method means allows bridges to compute their shortest path to this route. Of course, computing shortest path, you can do it in a centralized way with a computer, but the nice thing here is that this is all distributed. So there is no central controller in a network of bridges. It is every bridge comes, even the one you buy from Miko, comes with codes that automatically does all of this. So it will compute what is its shortest path to the root, and then only the links that are on the shortest path will be active. All the other links will be deactivated, will be disabled. Of course, there's also the number 3 in these items. I've explained this. So this poem explains points 1 and 2. The key thing is, of course, it must adapt to changes, to failures, or also addition. If you add a new bridge, perhaps you want to change the active topology. So all bridges monitor that the route is reachable. So every bridge has code that says, do all this thing that we said before. Plus, if you are the route, then every few seconds, you send a beacon. So you send a signal to all bridges. Since the bridges have built a tree, then it's easy. You send it broadcast over the tree. And then if you're not the bridge, listen for this signal. If after a number 3 or 5 times you have not heard this signal, that means that either the route is dead, or at least the path between you and the route is dead. So in that case, do it again. Do again what you do when you boot as a bridge. So all bridges monitor the spanning tree, and if they detect that it doesn't work, they will restart the computation. They will restart gossiping. They will say again, I am B1, etc. If B1 is dead, then B1 will not repeat I am B1, and then the other bridges will, via gossiping, learn a new route, and then they will also recompute the shortest path. This is how it is fully automatic here. To do that, you need to configure a cost. For example, here is a small topology on which I have a number of bridges. Costs are configured. Again, you don't really configure them. You can configure them, but this is also done by default. The costs reflect how much you would love these links to be on the spanning tree. So a high cost means that this link is less desirable. So the cost is inverse proportion of the bit rate of the link. The Ethernet links can be at 10 megabit per second, 100 megabit, 1 gigabit, 10 gigabit, or even 100 gigabit per second. So the higher the speed, the less the cost here. So we will conclude this session with a small quiz. If this is your bridge network, so you have these 6 bridges that are connected in this strange way, what will the spanning tree do? I close the poll. And here there's a clear majority for answer B, which is the correct answer. Here is what the bridges will do. In red, those are the links that will be active, and the other links will be disabled. How will they be disabled? In fact, either B5 or B4 will disable one of its ports, and it is as if it did not exist. So if A has a packet to send to B, when that happens for the first time, B5 will broadcast it to all the ports that are active. That means B5 will broadcast to, if there are other terminals connected to B5, it will send it. But here, if there's only A and B, it will simply send it to B1. B1 will broadcast it to B2 and B3. So the packet will reach all the bridges via the red spanning tree and will reach B. But after the bridges have learned, then the packets will always go only via the shortest path. For example, when B replies to A, the packets will arrive at B1 through its southern port. So B1 will think that B is on its southern port here. So the table, the MAC forwarding table of B1 will have this information. Voila, this is how the spanning tree works. We do a break and resume at 1:15.